Okay, welcome back. 3.7 is on related rates. Okay, so the idea is you're dealing with story problems. What you're going to do is read the question and basically fabricate an equation. Then you'll differentiate implicitly, then you'll sub in information. Okay. The problem, I think, is it's kind of like a multivariable issue. You have more than just x and y. You have x and y and t. Okay, so that I think maybe that's the issue that makes it more difficult. Um, and okay, so remember when you were differentiating implicitly, so maybe you had x squared plus y squared equals 9, and we wanted the find the derivative and do it implicitly, right? So you have 2x plus 2y, and then you always have to tack on this y prime thing, right? And then on the other side, I'd have 0. So that's one way to do it. And when we differentiate implicitly, it's kind of not explicitly said, but you're always you're always tacking on this thing to everything. So here it's 2x times the derivative of x with respect to x, technically. So you would have times the derivative of x with respect to x plus 2y, and the y prime thing is just the derivative of y with respect to y. Okay? And then out here, it's literally 0 times the derivative of x with respect to x. Okay? The deal is, though, the derivative of x with respect to x, and let me rewrite this notation so it's more clear what this thing is. It's the derivative with respect to x of x. Okay, in this notation, we're putting the x in the numerator. So what is the derivative of x with respect to x? Well, it's just 1, and that's why we don't write anything when we take the derivative implicitly. We're presuming that, sure, there is a 1 here, but we're not going to come out and say it. Okay, so in this, then this thing is really just 2x times the derivative of x with respect to x is just 1, so you just get 2x plus 2y times the derivative of y, this should be with respect to x. Sorry, hope that didn't just completely ruin my exploration. All right. Okay. So anyways, now, so this is before. The deal now is we're actually differentiating with regards to a third variable, which is time. Okay? So when I take the derivative, I'll have 2x, and then like here, you technically have to write dx with respect to dx, but if I'm differentiating with respect to t, I'm going to have to write dx with respect to t. Right? And then plus 2y times the derivative of x with respect to t, sorry, in this case then the derivative of y with respect to t. On the other side, the derivative of constant with respect to any variable is just going to be 0. Okay? Okay, so this is what I'm talking about. Now instead of just having x's and y's, there's this unseen t floating about that we are differentiating with respect to. So the x and y are functions of t. Okay? Some unknown functions, and we're taking their derivatives, and we end up with these things. And then they're called related rate problems. Right? Because we'll end up with equations that relate these two different rates. We'll solve them by using the information given, and okay. So hopefully that'll make it a little less painful. Let's go ahead and look at the first problem. And we have a point moving along a graph at some rate dx with respect to dt. They want us to find the rate of y with respect to dt. Okay, so we have a point moving on a graph at rate dx with respect to dt, and we want to find the rate of change of y with respect to dt. Okay. Okay, so the trajectory of the point is given by this parabola. They tell you the rate of change of x with respect to dt. Okay, the rate of change of x with respect to dt is going to be 2 centimeters per second. Okay, so how do we solve this? Well, you're going to take the derivative of this implicitly. Okay, so we'll have the derivative of y is 1 times the derivative of y with respect to dt equals, let's take the derivative of 2x squared, which will be 4x to the first times the derivative of x with respect to t, and then the derivative of 1 is just 0. Okay? One other thing we're going to need then is some sort of location x. Okay? Okay, so part A, we want to find the derivative of y with respect to t when x is equal to -1. Right? So what do you have? Well, you have two pieces of information, this rate of change of x with respect to t and then this x value. So we'll be able to solve out for dy or evaluate this. So we get 4 times -1 times dx with respect to dt is 2. And that'll be 2 times -1 is -2 times 4 is -8. So the rate of change of y is -8 centimeters per second. Okay. Part B then, we want to know the rate of change of y with respect to t when x is 0. So dy over dt is 4 times 0 times 2 centimeters per second. All right, so 2. Okay, so multiplying that all together, you get 0 centimeters per second. And that's about the tall and the short of it. All right. So that's a simple version of the problem. Let's look at the more complicated versions now. The first couple of problems we'll look at are geometry type problems, and then maybe we can look at more of a physical, real world type problem. Okay. Okay. So number 11, the radius of a circle is increasing at a rate of 4 centimeters per minute. Find the rate of change of the area of a circle when part A, r, the radius is equal to 8, and then part B, when the radius is equal to 32. Okay, so first you want to form an equation that kind of relates everything. We're after at the end of the day is going to be the rate of change of the area with respect to time. Okay. We're given the rate of change of the radius with respect to time. So we want a formula that's going to relate r, radius, and a. Okay. And so we're talking about the area of a circle, so we have a formula for that from geometry, in particular a equals pi r squared. Okay. So to then what we're going to do with this formula is take the derivative implicitly, and we'll have these terms in it. So the derivative of a with respect to t equals pi times the derivative of r squared with respect to t. So that's 2r times the derivative of r with respect to t. Okay. So part A, we're given r is 8. So you just plug that into this formula along with our rate of change of the radius. So the rate of change of the area will be pi times 2 times 8, which is 16, times the radius of change, the rate of change of the radius, which is 4 with respect to time. So we'll end up with 64 pi centimeters squared per minute. And then obviously for r equals 32, you just do the same game. So the rate of change of area with respect to time in that case will be pi times 64 times 4. And so in that case, 256 pi centimeters squared per minute. Okay. Let's look at a sphere version of this problem, the spherical version. So this time the radius of the sphere is increasing at 3 inches per minute. Problem 13 in the book. So the radius of sphere is increasing at 3 inches per minute. Okay. We want to find the rate of change of volume when the radius is 9. Okay. Part A, find dV with respect to t when r is 9. Okay, so we're given the rate of change of the radius, so dr with respect to dt is 3 inches per minute. Okay, we need a formula to connect r to v, so that's easy from geometry. V is equal to 4/3 pi r cubed. And then to get a related rates formula, you just take the derivative of this with respect to t. So we have dv with respect to dt is equal to 4/3 pi times 3r squared times dr with respect to t. And then we should just be able to plop in our information. So when r is 9, we'll get 4/3 pi times 3 times 81 times dr with respect to dt is 3. Okay, the 3 here cancel. 3 times 81, 273, and then times 4 is 972. Okay, and then the units were in inches cubed for volume per minute. Okay. So note, one thing to note is that the rate of the change of the volume is increasing much more rapidly than the rate of change of the radius itself. Okay. Anyways, let's look at number 19. Let's keep moving. Number 19 is this, it's like a pool, and you're filling the pool with water, and you want to know the rate of change of the height of the pool for whatever reasons. Okay. So we need a picture. This is number 19 in the book. You may want to look at the picture. I'll try to draw it out. Water is being pumped into the thing at 1/4 meter cubed per minute. Okay. What is that then? That's the rate of change of volume. So this 1/4 meters cubed per minute is really dV with respect to dt. Okay. We want to know eventually the rate of change of the water level. Okay, so we'll define some extra variable and make a relationship and then implicitly differentiate, and we'll have a related rates problem. So the pool is kind of weird in that it has two kind of volumes to always take into consideration. There's this rectangular solid region, and then below it there's this sort of triangular region. I'm trying to draw it best I can. In the beginning, it's kind of partially full, so you have a bunch of liquid right here in the pool. So what? They give you some information. They're telling you this dimension here is like 1 meter. This dimension here is 6 meters. And this depth here is 3 meters. And this distance here is 12 meters. I think that's really all they say. The pool is initially filled 1 meter deep, so this is 1 meter. Okay, I think that's all they give us. If not, I'll sort of adjust. But part A, they want to know what percent of the pool is full. So how do we get through this part of the problem? We want to make a ratio, basically what's the total volume in the denominator, and then the numerator, just find the volume of this region, the water region. Right? So the volume of the pool is going to be the volume of this cubic region, this rectangular solid region, plus the volume of this triangular type region here. Right? Add that in there. Okay. Right. So the volume of the rectangular solid is just 6 times 1 times 12, length times width times height, basically. And then plus the volume of this region down here, you multiply this triangle area times 6, and that will give you the volume. So it'll be 6 times 1/2 times base, which is 12 times height, which is, well, if this is 3 and this is 1 and this is 1, this distance is 1, and so therefore this distance is 2. So multiplying and adding, you get 144 meters cubed for the volume of the pool. So then we need the volume of the water. And the trick to these kind of problems is figuring out, using similar triangles to figure out things. So in particular, if we kind of extract this triangular region and take a look at it, we have this distance. Okay, so that's this distance from here to here, and that's 2. We have this distance, which is 12. And then we have this other triangle embedded in it, and the distance from here to here is 1. In order to get the formula, 1/2 base times height, we're going to need this distance here. So we use similar triangles. Okay, and we're going to call this distance, I want to be careful here because I'm going to use this variable again. I'm going to call this distance y. Okay. Maybe we should probably call it x, but yeah, let's call it x. Okay. Okay, so I make a ratio of the sides. So 1 is to x as 2 is to 12. Right? So 1 is, this side is to this side as this side is to this side. And then cross multiply, you'll get 2x is 12 right? And then that tells me x must be 6. Okay, so the volume of the water of the is 1/2 base, which is 6, times its height, which is actually the depth value, which is 1. And then times this other dimension here. This dimension will give us the volume. So that value is 6. So it's area times this dimension will give you volume. Okay, so 1/2 base times 3 times 6 is 18. And therefore, the percent of the pool that's full is 18 all over 144 times 100, right? So that would be, in particular, 12.5%. So it's times 100%. So not much. Okay, so moving on then. We want to know at what rate is the water level rising. Okay, essentially then, if we think about this, the side view again of the pool. Oops. So I have this 2, and then right now this is at 1, but it'll be changing, right? So let me redraw this. It's going to be too close. Okay, so right now the depth of this triangular region is 2. It's currently at, so I need a variable for the water level, and that's I'm going to call that y. Okay, so this is going to be y. Here this will be, I'll call this x. These are constants. This is 12. Okay. I want to know the rate of change of y with respect to time, right? So I want to know the rate of change of this water level with respect to time. So I need a formula that relates everything. So I want, I'm given this value, this volume rate of change, so they're pumping water in it, and the level, the volume is changing at 1/4 meter cubed per minute. So I need to relate volume to this rate of change of y. So volume as it sits, and we kind of can leech off of our work over here, so we're going to need some similar triangles and stuff. The volume will be 1/2 base, so I'm looking for the volume of the water in the pool, formula for that. 1/2 base times the height, and then times the depth. So 1/2 base times height times 6. This will be 3xy. The only trouble with this thing, though, is that x is also unknown, but you can use similar triangles to get rid of x. So note over here, y is to x as 2 is to 12. Okay? And then cross multiply again. 12y equals 2x. And then we can eliminate x by dividing both sides by 12. Did I do that wrong? So y is to 12 as, no, y is to x is 2 is to 12. Y is to x is 2 is to 12. That looks good. 12y, I'm solving for x. Okay, so I need to get rid of the x in this equation. Sorry about that. So if I divide both sides by 2, I get x is 6y. And I get rid of it that way. So my volume equation is going to be 3 times 6y times y. And of course, that will be then 18y squared. And then I can go ahead and get the related rates problem. dv with respect to dt is going to be 36 So it's 2 times y times the derivative of y with respect to dt. So it's 2 times 18 is 36, and then I have y, and then I have times this dy with respect to dt. Okay? So I'm given that the rate of change of the volume is 1/4. Okay? The right-hand side is 36y times dy over dt. The water level is currently at y equals 1. If you go back to our picture, it's given in the book that the water level is initially at level 1. So I could replace y with 1. So currently y equals 1. So we get 1/4 equals 36 times 1 times this unknown rate of change that we're after. Divide both sides by 36, and so you get the rate of change of the depth of the water is equal to 1 all over 144 meters per minute. So it's really changing in a slow way. Okay, so anyways, there's that, the pool problem. So it's still kind of a geometry problem, but at least a little bit more realistic. Let's now consider definitely a more realistic problem. So you can imagine this is the kind of problem you'd have if you're maybe I don't know personally, but if you were a air traffic controller, maybe this kind of thing that you would worry about at night. You have two planes quickly approaching each other. One's location is at 0, 300, and it's moving at, I believe, what does that say, 600 miles per hour in this direction. And then you have another plane located at position 225, and it's moving at 450 miles per hour. Okay, so the problem is they're going to collide once they get to here. This thing's moving 600 miles per hour. In a half hour, it's going to be at position this position 0, 0. If this is moving 450 in a half hour, it's going to go 225 miles. So it also will be at position 0. In fact, in part A, they want to know how long until the planes collide. Or maybe that was part B, I don't know. But you can kind of see just by looking at the graph, how long until planes collide. That's just going to be 1/2 hour. Okay. So anyways, part B, what rate is the distance between the planes decreasing? So and what they're considering then is this distance. Right? At what rate is the distance between the planes decreasing? Okay, so we're given kind of a rate of change and y with respect to t, like negative 600 miles per hour. We're given a rate of change of x with respect to t. That's the other plane. That'll be negative 225 miles per hour. We want a formula that tells us the rate of change of this distance here. Okay, so you can relate all of these variables, the x, the y, and the d, using the distance formula. So d is equal to the square root of x, I guess x minus 0 and then y minus 0. So this point is 225, 0, and this point is 0, 300. And in general, this will be the point 0, y, and this is the point x, comma 0. What do we have then? In the distance formula, x x2 minus x1 will be x minus 0 squared, and then plus y2, 0 minus y1, so 0 minus y squared. And at the end of the day, that's square root of x squared plus y squared. Okay. We can get this, we could solve out for the rate of change of d after squaring this equation. We'll still be able to find a nice formula for the rate of change of d. Let's call d something else, because if I call it d, I'm going to have dd, and that looks a bit silly. So let's call it s. Okay? So this will be s, and this will be s. And then square s, so you get s squared is x squared plus y squared. Okay? And then we'll differentiate implicitly. We have this information, we have kind of an initial condition that we can plug in order to figure out the rate of change of the s value, the distance between the two. So implicitly differentiating, I get 2s times the rate of change of s with respect to t, so ds over dt. On this side, I get 2x times dx with respect to dt, plus 2y times dy with respect to dt. You can divide out by 2, so you get s equaling, or s ds over dt. I'm going to want to divide by s as well, so I might as well do that all at once. This will equal x times dx with respect to dt plus y times dy with respect to dt, all over s. So I just need to fill in the blanks. I have kind of an initial condition, 225. So my desired values, I guess, to be plugging into this related rates formula, we have x is 225, y is 300, s then will be the square root of 225 squared plus 300 squared. If you put that, and I'm just using this formula to solve for this s value, putting that into my calculator, I get 375. Okay, I already know the velocities of the airplanes, so I got airplanes, so I can put those into this equation. And so the rate of change of the distance between the planes at that particular moment is going to be 225 times negative 600 plus 300 times negative, whoops, I accidentally put the rate of change of the other guy. So it's 225 times negative 600, and then 300 times negative 225, and then that's all over 375. And we need to put that into our calculator. I'm getting negative 750 miles per hour. Okay, so a much more realistic example of related rates problems. Okay, thanks for watching. Bye.